everyone! Remember these guys? Today we're going to be talking more about modular multiplication tables. If you haven't seen my previous video on these, I definitely recommend watching that one before this, especially if you have no idea what these pictures are. But for those of you who have seen the video, a little refresher for you. Modular multiplication tables are created with two numbers, the modulus and the multiplier. We'll denote these with the letters M and A. To create a modular multiplication table, we just take a circle and split the circumference into M points. Then we connect each point P to P times A mod M. So last time, we mainly explored the questions, how does the modulus affect the table, and how does the multiplier affect the table? But today, we will be looking at how M and A work together to create the picture. To begin to answer this question, we'll be looking at different classes of relationships between M and A. You'll see what I mean. The first class that we'll be looking at is when the multiplier is half the modulus, or when A equals M over 2. And we're assuming here that M is even, so A is a whole number. To get started, let's look at some examples of these types of tables. You can see that they all have a very similar structure. They have dark spots on the top and the bottom, and lots of diagonal lines in between. If you want to think through why this might be for yourself, go ahead and pause the video now. So to understand why this happens, let's choose a random point on the circle, P, and consider where P times A will land. We can think of P times M over 2 as going halfway around the circle P times, starting from 0. If P equals 2, then we'll land at 0 again and make a full rotation. If P equals 3, then we'll make 1.5 rotations and land on M over 2. It's not that hard to notice that if P is even, then P times A will land on 0. And if P is odd, then P times A will land on M over 2. So every point around the circle will either be connected to 0 or M over 2. And that's why there's a dark spot on each pole. If you recall my previous videos on modular arithmetic, you can think of what's going on here through that lens. If P is even, then P equals 2n for some number n. Then M over 2 times 2n equals M times n, which is congruent to 0 mod M. And if P is odd, then P equals 2n plus 1. And doing some algebra, we see that P times A is congruent to M over 2 mod M. So again, the binary mapping of every point to either 0 or M over 2 creates the pattern that we see in the tables of this class. The second class we'll be looking at is when A is one more than half the modulus, or A equals M over 2 plus 1. Here are some examples of this class. Again, they all have a very similar structure, almost like a wheel. If you want to think through this one for yourself, go ahead and pause the video now. To understand why this is happening, we'll use the same strategy as last time. Pick a random point P around the circle and see where A times P lands. If we follow the algebra through, we see that A times P equals M over 2 times P plus P. Now, we know where M over 2 times P will land because of the first class that we looked at, either 0 or M over 2. So, if P is odd, then P times M over 2 will land on M over 2, and going an extra p points around the circle will be directly across the circle from p. Now, if p is even, then p times m over 2 will land on 0, and adding an extra p points will just bring us back to p, so we don't need to draw a line. So a times p will either land on p if p is even, or m over 2 plus p if p is odd. We can again think through this in terms of modular arithmetic. If p equals 2n, then p times a equals 2n times m over 2 plus p, which is congruent to p mod m. If p equals 2n plus 1, then we can follow through the algebra and see that p times a is congruent to m over 2 plus p mod m. Because odd points are connected to the diametrically opposite point, and even points are connected to themselves, we get this wheel-like structure. The last class that we'll be looking at today is when a is 1 less than half the modulus, or when a equals m over 2 minus 1. Here are some examples of this class. You can see that each of them makes this grid-like pattern. Go ahead and pause the video now if you'd like to figure out why this pattern happens for yourself. If a equals m over 2 minus 1, then we can see that p times a equals p times m over 2 minus p. Again, we know that p times m over 2 will either be 0 or m over 2 because of the first class that we looked at. So first consider if p is odd. Then p times m over 2 will land on m over 2. Now go backwards p points around the circle. This brings us to a point that is reflected across the horizontal axis from p, creating a vertical line. Now, if p is even, then p times m over 2 lands on 0, and we go backwards p points around the circle from there. This lands on a point that is reflected across the vertical axis from p, creating a horizontal line. I'm showing both an example of p less than m over 2 and p greater than m over 2, so you can see that this argument is generalized to any p around the circle. Either way, we get vertical lines if p is odd and horizontal lines if p is even. Now, let's take a look at the modular arithmetic. We can see that if p equals 2n, then a times p equals 2n times m over 2 minus p, which is congruent to negative p mod m. If we draw a picture of p and minus p, we see that geometrically, a line between the 2 points is always horizontal. If p equals 2n plus 1, then a times p equals 2n times m over 2 plus m over 2 minus p, which is then congruent to m over 2 minus p mod m. Again, drawing a picture, it makes geometric sense that a line between p and m over 2 minus p will always be vertical. So those are the classes that I wanted to look at today. We're going to do a little bit more with them in a minute, but first I wanted to talk about some broader ideas. In my first video on modular multiplication tables, we looked at what happens when a equals 2, 3, 4, and so on. And now we're examining a whole group of a values at one time. This is a reflection of a bigger concept in math. Oftentimes when you're faced with an unknown object, it helps to take an approach that goes from the specific to the general. Looking at specific examples provides an access point, And then, as we generalize, we get closer to understanding. This is how I began to understand modular multiplication tables. So now that we're looking at different classes of relationships between A and M, the next question would be, how can we generalize those relationships? There are probably a few different ways, but the first step I thought of was to look at divisors other than 2. So instead of considering when A equals M over 2, let's look at when A equals M over B, where B can be any whole number, not just 2. We will still assume that B divides M because we want our A values to be whole numbers. So then, our 3 classes become A equals M divided by B, A equals M divided by B plus 1, and A equals M divided by B minus 1. These generalizations are now sets of classes. In a way, they are meta-classes. They contain the classes we are just looking at, but also infinitely many other classes of tables. Instead of looking at patterns between tables that share a common feature, we will be looking at patterns between classes of tables that share a common feature. Here are some examples of each meta-class with different B values. Now it's your turn. For each of these classes, ask yourself, what's the pattern and why does it happen? I will leave the answers to these questions up to you guys. A few minutes of thought should start to bring the explanation to light. I recommend going from the specific to the general. First, look at when B equals 3, and then B equals 4. And now, what can you say about the rule for any B? Draw some pictures and see what happens to various points. And then, if you're still hungry for more, what other classes and patterns and generalizations can you make? I will leave a link in the description to a site that will draw these tables for you, so you can start exploring for yourself. So that's all I have for you guys today. Next time we will expand on these ideas even further and think about what other factors influence the shape of modular multiplication tables. See you all next time. Thanks for watching and keep exploring.